I am Mohan Poteri. I'm a staff solutions architect. We're going to talk today. We're going to talk about a project called VMware Data for Good. We are here. We hope to showcase how we can use a VMware Cloud Foundation platform to host machine learning platforms for data scientists that nonprofits can bring on board and leverage to gain insights into their data. Andre, why don't you introduce yourself?
Hi, I'm Andrei Neverov. I'm a staff engineer here at VMware. I work as part of CPBU on VMware Cloud Foundation. And I'm happy to present today together with Mohan and show you a live demo later on.
So today's agenda, we'll talk about the initiative. We also talk about the VMware Cloud Solutions Lab. The reason being that this is the lab where we are doing this Data for Good program. That we show you the capabilities of this lab, and then we kind of look at how VMware Cloud Foundation enables AI ML. Then we look at the logical architecture of the solution. We talk about the vMLP platform, an internal VMware solution that is also Fling available for partners. And then we do a demo and then conclude. So let's get started. So the Data for Good initiative was inspired by Pat Gelsinger, who spoke about tech as a force for good. We can use tech for a lot of things, but we need to consciously try to use it as a force for good. And he spoke about it and introduced this concept in VMworld 2019. So that is what inspired us. We have a high-profile lab, and then we want to see if we can use the resources of this lab for a project that can help nonprofits, and that's kind of this project. The VMware Cloud Foundation, as you know, has a lot of capabilities. It's got vSphere. It's got all the SDDC components, and it can be leveraged in a way where we can run a ML/AI platform in a very effective manner. And then the hardware we have in the lab has got GPUs and other capabilities, so that will be leveraged. And a lot of them have been donated by partners. And then we also have petabyte scale storage, which we will leverage in this project. So the lab's model, right? We typically have this lab where we collaborate with hardware partners, but typically who contribute gear to this lab. VMware manages the lab. VMware buys the servers for this lab. And then we propose projects and solutions that highlight areas in the industry that would be good solutions to showcase. And so we propose, collaborate, and then produce content. And a lot of the stuff we produce are shown here as links, and those links are where our solutions that we build in this lab. So some of the partners here that we use, and so these are the partners that have provided us gear. And we also have on the right-hand side, you see cloud partners. So this is actually a cloud lab. That means there is an on-prem piece, and then there's a lot of cloud providers connected to it. And so in the future, the cloud partner part is a little bit new. In the future, we're gonna have connectivity to all these partners, like cloud partners, and be able to migrate workloads back and forth and have a truly hybrid / multi-cloud environment. So this lab is pretty robust in that situation. And we also have a lot of hardware partners, as you see, that provided high performance infrastructure that we will leverage for this project. And then this lab has been there since 2017. We have there's something and it's been there, and then we do almost like 25 projects a year. We have a lot of collateral that we develop, 50 to 75 pieces of collateral, and those are the collaterals that will show up in those links that I showed earlier. And so what do we have in the lab? We have almost 40 servers, 2,400 cores, 20 terabytes RAM, and so you can read through this, but there's a lot of CPU, GPU, FPGA, high performance storage, petabyte scale storage, high performance networking, um, traditional networking with Brocade, and high speed networking with Mellanox. And then we have all these cloud providers. So imagine having this as a playground to build solutions, and that's kind of what this lab has. So this is a because this, a lot of it is made possible by partners, and we have more than multi-million-dollar worth of assets here in this lab. And so, we hope to showcase this project so that our VCPP partners can potentially use the capabilities that we showcase here and build their own service, maybe in MLAI. It could also be for partners who want to show their customers how to build this or use it, right? So that's kind of what the goal of this project is. It will be like an example project where we are using VMware software along with high performance hardware to offer a data science platform. So now let's look at some of the aspects of the ML on the VMware platform. For Pat Gelsinger, machine learning is the most important new workload to emerge in enterprises in the last 10 years. So that is pretty obvious to all of you, because you can see a lot of the areas being slowly being addressed with machine learning, even though there's a lot more to go, but it is growing, and you can see by the potential in the market. You can see that it's growing many-fold from 2018 all the way to 2025, and so this is a good market to focus on and address. And that's kind of that is why we wanted to do this project, so that this could be something service that the partners can potentially offer their customers. And if you look at ML, right, it is actually a small piece of a bigger data puzzle. So if you think about it, there's a lot of aspects to data processing that happens before and after machine learning or deep learning training, for example. So that's kind of what this shows you. And all these aspects can be addressed by VMware infrastructure using VMware Cloud Foundation. So today we are focusing on the ML piece, but there are other solutions that we are building that we will highlight other aspects of data processing. So let's some of you might have already seen some of these aspects addressed earlier, but we just wanted to brush through some of the accelerators that we support, and how in the VMware environment you could use GPUs, for example. So for GPUs, GPUs are the one of the biggest accelerators for machine learning and deep learning. So that's why we are addressing it. We in the future hope to address other accelerators like FPGAs and other tools as well. GPUs, for example, can be accessed in 3 different ways in a VMware environment. Direct path I/O. Almost every hardware out there can be used through direct path I/O, because the VM is directly connected to the hardware. The hypervisor just passes it through. So there is no drivers or anything special needed on the ESX layer. Everything is done at the guest, and it'll be almost like bare metal. NVIDIA vGPU is the methodology that NVIDIA has developed. They provided a VIB on top of the hypervisor. The VIB is installed on the hypervisor, and it helps mediate connectivity between the guest OS and the GPUs. And you can have many methods of access. So you can have partial GPUs, full GPUs, and multiple GPUs in this methodology. The good thing about NVIDIA vGPU is that all the traditional VMware features like vMotion HA and all that will continue to work. With direct path I/O, since the VM is directly connected to a piece of hardware, those capabilities are not available. Last but not the least is Vsphere Bit Fusion. VMware acquired this company Bit Fusion almost a year and a half ago, and we've made it part of the Vsphere family. And so the Vsphere Bit Fusion is unique in the sense it allows you to access GPUs over the network. So for service providers who have a lot of compute out there and who don't have GPUs on all the servers, you have a capability to expose the GPUs over the network to your workload. So that is what Bit Fusion provides. And in this project, because it's more like a developer data science platform, we would be actually showing you Bit Fusion. So, but there are multiple methods, and what I'm hoping to show you here is that the VMware Cloud Foundation platform is very flexible, and as you know that VMware came about its popularity through virtualization of CPUs. So initially there was like CPUs were underutilized, and VMware came about and made sure that there's more utilization. We created this whole industry around virtualization. So now GPUs are also in the same situation. They are underutilized in the enterprises, and so a lot of times they're not virtualized, and because of that, only like a few engineers get access to a GPU, and then there's a lot of inefficiencies over there. And with running GPUs on a virtualized platform, you're able to kind of share it across multiple users and make it more effective. And also, one important thing about GPUs is that GPUs can cost quite a bit, and they could cost as much as a server. So it is more important that you share, provide capabilities to share the GPU, so that to make sure that you're using it, putting it to best effect. So let's talk about modern compute infrastructure to some extent, because this kind of will lead you into how we have architected the solution. So if you think about how the modern data center is evolving, you will see that there are all these different types of apps that are running. There's the legacy apps coming from the client server world that is slowly, there's still a lot of it is still there. There's the modern apps that leverage Kubernetes that are taking off. And then you have hardware, and the hardware, as I said, has a lot of things changing. A lot of new accelerators are showing up, different networking cable technologies, high speed FPGAs and other aspects are showing up. So there needs to be, the data center now needs to include all of these components, and all of these need to be able to coexist with each other. So that's what the VMware Cloud Foundation provides you. It provides you the ability to run legacy apps, the ability to leverage the advanced hardware out there, and to run Kubernetes. Because if you think about it, for modern architectures, containers are the new kernel. And then there's a lot of hardware that a lot of partners and customers have invested in. And so we want to continue to leverage that, but able to run all these things in a converged fashion. And so that's kind of what our platform provides. And just earlier this year, we introduced the VMware Cloud Foundation 4 with Tanzu. Tanzu is our Kubernetes platform, and then it provides many ways of accessing Kubernetes. There is a Kubernetes that is embedded in the ESX kernel. There's a Kubernetes that runs as a service, as a guest clusters. In our situation, we'll be using the Kubernetes as running as the guest cluster, and you're able to leverage, all this is able to leverage vSphere, NSX, vSAN, any VMFS, all the different things that VMware has developed over the years. So you kind of layer on top of what we already had, these new modern app capability. And then the hybrid cloud platform. So if you think about the vision we have, is that customers could have their own data center, they could be managing it. Then there's VMware Managed Cloud, VMware Cloud on AWS is an example. And then there is partner managed clouds, right? There's Azure VMware Services, there's Google Cloud, there's Oracle Cloud, there's Alibaba, there are also 4,000 VMware VCPP partners. So all these, you can see it at the bottom. So all these solutions we want to is based on the VMware Cloud Foundation. The base is pretty similar between them. There will be a few variants based on the capabilities of the different cloud providers, but in the end, our whole goal is to make it ubiquitous. You should be able to run your VMware infrastructure anywhere, right? And so that's kind of this is the foundation. This is what VMware Cloud Foundation is what we'll be leveraging for this project. So Bit Fusion, right, was introduced in vSphere 7 as well, and it provides you, as I mentioned here, is you can see that you can have VMs, containers, Kubernetes with no GPUs on the left-hand side. If you think about it as a compute cluster on the left and a GPU cluster on the right, so you take all your GPUs and then consolidate them onto a GPU farm, and then you leverage Bit Fusion to provide access to them over the network. For a high performance need, you might need to have a higher performance network connectivity. So for certain workloads that need high performance, you might want to provide RDMA based RoCE connectivity, so that we do support RDMA and RoCE for 100 gigabit Ethernet. So that could be an option when you really want to have high performance with Bit Fusion. So again, here are the pros and cons of Bit Fusion. We chose Bit Fusion because of the type of project we are running, and so it's good. It comes with Enterprise Plus with an add-on or add-on entitlement that you need, and then you can have multiple GPUs, fractional GPUs, HADR, vMotion for the client VMs are available. And it optimizes the CUDA API, which is part of NVIDIA's software framework. The only thing, as I mentioned, network latency is a potential bottleneck, so you should design accordingly. It is also right now only GPU only. We plan to enhance it to support FPGA and ASICs in the future. And the thing here we're showing here is that it is embedded embedded into the vCenter, so you're able to look at all your GPU resources, the clients that are using them, and you're able to manage them. So that's kind of what Bit Fusion brings here, and that's what we would be leveraging in this project. So now let's look at what we have to build for this Data for Good program, what we use to build our solution. So we have compute nodes that are running the Dell R640 servers, and then we have accelerator nodes that have Dell R740 with NVIDIA Tesla T4 GPUs. So those will be part of the GPU cluster. And then we are running VCF4 with vSphere 7. We have vSphere Bit Fusion. We are running VMware TKG Plus. That's the Kubernetes platform. We are using the entire platform. Entire solution is deployed on Tanzu Kubernetes Grid, and we're leveraging NVIDIA CUDA with Bit Fusion here. And from a networking perspective, we have regular networking, 10/25 gig networking for the servers. Then we have Mellanox 100 gigabit RoCE networking for high-speed needs. And then we have, since this involves a lot of data, we have a petabyte InfiniDAT storage that we're leveraging, and it can both do NFS and a fiber channel SAN. So we're combining all those capabilities and building a platform. And so this is kind of how a GPU cluster is aggregated. So we have a lot of GPUs that are aggregated, and then we have a dedicated cluster, and Dell R740 is what is being used, and the T4s are being, the NVIDIA T4 GPUs are shared out by the Bit Fusion. If you look at the logical architecture, this is how it looks like. So we have, on the left-hand side, you have Tanzu Kubernetes Grid plus compute cluster. So it's running on top of vSphere 7, and you have all these Kubernetes pods that are deployed on this platform. The pods that are running are the vMLP platform that Andrew will be talking about shortly. And on the right-hand side, you see the GPU cluster. And then basically, we can scale the compute cluster as and when needed, and also increase capacity on the GPU side as and when needed. So initially, to start off, we have a single cluster that is dedicated to the Tanzu Kubernetes Grid Plus, and then a single cluster for GPU and a Bit Fusion based cluster for GPUs. So this is kind of how is like a good building block. You can scale up from it based on your user needs and the amount of usage. You can scale up or scale down. So, and now with that, I'm going to pass on to my partner Andre to talk about the vMLP platform.
Thank you, Mohan. Yeah, so vMLP stands for VMware Machine Learning Platform, and this is the project started a couple of years back. So I myself used to be a data scientist here at VMware for some time, and we experienced a lot of pain points back then as a data scientist, specifically related to the infrastructure, right? So the types of problems where, let's say, we start a new project, we discover some new library, some deep learning library, and then we need a GPU. And the question is, okay, how do we get GPU to work, right? There's like multiple layers of dependencies, all the way from ESXi to like Kubernetes, to how Kubernetes handles GPUs, all the way to the libraries, drivers, CUDA, and then our, let's say, TensorFlow or PyTorch. So another set of problems was that, how do new people get started on the project, right? So when they start doing their work, they kind of face the same issues again and again, right? So how do we resolve this? How do we make sure that we have a consistent workflow within data science so that people can get repeatable results, right? So we started to think about it and basically came up with this vision that we want to increase impact of data scientists' work by letting them focus on AI and ML, and also efficiently use their specific skill set instead of fighting broken infrastructure, right? And so to resolve that, we basically came up with an end-to-end machine learning platform, which seamlessly deploys and runs AI ML workloads on top of VMware infrastructure. Right, and by doing so, there's like some of the benefits right off the bat is that it's very cost efficient, right? Because like you can have less GPUs and enable efficient use and share them between data scientists. We also reduce risks of these broken data science workflows because we standardize on what we do. Another thing we introduced is that a faster go-to-market for AI/ML models, right? So this is within the organization. There's typically a data scientist, and data scientist has a end consumer, right? So some sort of apps here, which require, for example, results of inference, some prediction of some values. So how do you even deploy this model so that these consumers can consume as soon as the model is available? And again, doing it in some standardized way, like which everybody is used to, like REST API, right? So we do that by offering a number of capabilities here, right? So first and most importantly is that there is a environment, virtualized environment, which deploys well on VMware and Kubernetes. That environment gives us access to Jupyter Notebook, right? Specifically to Jupyter Lab 2.0, which is pretty much a standard in the open source community, and pretty much majority of data scientists know how to work with that. The platform itself is also based on Kubeflow, which is open source project from Google, and leveraging some other well-known open source components like Horowat, which is a distributed machine learning orchestration framework. So this capability, Kubeflow and Horowat, gives us ability to train models on the cluster in distributed fashion, which is good for large models and leveraging things like GPU. So the GPU support is plumbed all the way through from ESXi to to our notebooks, right, passing through Kubernetes. And as Mohan mentioned previously, there are 3 ways to consume GPU. So vMLP is compatible with all 3. But for today's demo purposes, we picked Vsphere Bit Fusion since it allows us to demonstrate most components. So then once this training process completes, which is orchestrated by vMLP, the model ends up in a model repository. So this is done for reproducibility reasons. There, it's very easy to search for a particular run and see what were the parameters, the metrics, and even get the model artifact. And last but not least, as I mentioned, we want to actually provide some value for the end users. And so we made it very easy to deploy those models from the repository into the serving cluster. Right, so in the serving cluster, a model turns into a REST API endpoint, which end users can simply contact, right? In many cases, just using curl, or it could be some very simple program. And we build an advanced POC, which I'm going to demonstrate in a second, and we released it as a Flink. So here, please see this link where you can download the Flink and give it a try. Next, please. Yeah, so to demonstrate this, we decided to use the VCSLAB and Data for Good project as an example. And that fit quite well because the infrastructure was ready. So we have high-end servers, high-speed networking. We have Kubernetes, GPU support. Bit Fusion deploys on vSphere quite easily. And so all these prerequisites for us, Kubernetes, load balancers, storage is met very well by VMware Cloud Foundation platform. Yeah, and so I'm going to demonstrate some of these benefits I mentioned today in a live demo. So as I mentioned, we are based on kubeflow, right? So here, when a vMLP deploys, we can see the service running. So this is an example of an endpoint which exposes kubeflow UI as a main UI. And then from there, we of course have the underlying components, which I'm gonna go into a little bit more detail. Okay, so let me share my screen now. Okay, so let me start by introducing the infrastructure piece. So this is a primary vCenter for the VCSLABs, and what we have here our HPC2 cluster and our resource pool. So here we can see a number of VMs which represent Kubernetes. So first one is the Kubernetes master, and we have 4 workers here. So let me switch to the Kubernetes view. Let me demonstrate you how this works. Yeah, so basically this is the Kubernetes view, which is corresponds. So we also see a master here, and we see 4 workers. Then vMLP has been installed using our installer. So we actually have a few ways to install it. One is a web-based UI installer. One is Kubernetes operator, and one is a set of scripts for fine-tuning various internals. So once we run that, we get this a number of additional namespaces. The most important one being the kubeflow itself. Then we also deploy Istio to take care of API gateway and authentication. In this setup, we deploy DEX as our IDP solution. And then we can see here there's a number of namespaces which the system creates for specific users. So let's look at the main kubeflow namespace. So we can see here it's actually a quite complicated system, right? So it's a number of microservices taking care of various components. So we can see here there's and these are both machine learning specific as well as some enhancements we did over the open source kubeflow to sort of make the workflow more rich and smooth and sort of adapt it to our infrastructure. So a good example for that is that, for example, we can see here a LDAP pod, right? So we deploy, vMLP allows to optionally deploy LDAP on the cluster. So other things is that there are vMLP specific components, like there's a live documentation server, there's some like additional storage components. There's the MLflow. This is another open source project used for model storage, which is not part of Kubeflow, but we found it superior at the moment, and so we integrated the two. And the rest is pretty much standard Kubeflow components, right? So vMLP installer orchestrates deploying this in the right way, right? And so once we do it, once the installer runs, thanks to our infrastructure, we easily get the load balancer to provide us some endpoint IP address here. And so I'm going to switch to that and show you how the data scientists would experience this system. So once they go here, they will be, obviously they are not logged in, so they will be redirected to this authentication flow, and I'm going to use the LDAP component, which we optionally deployed. So there's multiple ways to configure, but this is we saw this is most convenient because this is a public cluster. So here again we see the Kubeflow UI, pretty much the standard UI. I'm going to show you various capabilities, right? So first, this is the sort of the primary endpoint for data scientists is to create and use notebook servers, which is basically their IDE for doing data science work. So here, this is a Jupyter Lab 2 environment, and I'm going to show you, to demonstrate you how we can leverage Bit Fusion for machine learning. So here we have a project, right? And these projects we generate, right? So so that it's done in a very consistent way. The only thing I needed to do is that I uploaded the Bit Fusion files so that this environment knows where to run. And then, so this is example of PyTorch-based code, which is pretty much taken out of the GitHub. So there's no special magic here, which is great. So it makes this solution good for many use cases. And so we did some enhancements. For example, I'm going to highlight this cell, and I'm going to go to this train plugin here, which we wrote, and I'm going to start this job, right? So notice that here I do not provide GPUs. Do not specify how much GPUs we want, because this cluster actually doesn't have a direct pass-through or NVIDIA GPUs, but it does have Bit Fusion, right? And so we will see that when the job runs, it will actually leverage Bit Fusion, right? So here I'm starting the job, and the job is going to be transferred to the cluster. So let me just copy this ID. Right, and so we see, so we have provide some API how we can track the jobs on the cluster, and so this is going to run a few minutes, but in the meantime, let me explain what it will do behind the scenes, right? So right now it's actually building a container on the fly to include our data science code, and it ships it into the cluster with accordance to the resources we configured, and we are going to navigate to Bit Fusion here. So what we expect to see is that, so basically we have our cluster, right? And this is like a consumption. So we can see that pretty much at this point of time, it's unallocated. So we have total of 4 GPUs and none of them are used. We see a little bit bump here. This is sort of, we did a pre-testing before this demo started. But hopefully we see it tomorrow, also in when the job starts on the cluster, right? So this is our list of servers. We can see that some of them have 1 GPU card, some of them have 2, and this is our list of clients, right? So let's see. So let me switch to a shorter time window here, and yep, let's give it a moment. So in the meantime, I'll show while this is running, I'll quickly show what else happens. So the model, while it's running, it's going to be saved into this MLflow model repository. So here is example of the previous run, which we did as part of pre-testing. So if I navigate here, we can see all the information about like when it was run, by whom, and like we have a possibility to enter any parameters for the model, and then there's some like metrics which the model output, and here there's some artifact. So specifically, like this file here is actually a binary version of the model. And again, this is leveraging all our storage capabilities. So this model repository is deployed on top of our storage class, right? So which is managed by Kubernetes storage plugins. Okay, let's see if anything happens here.
While waiting, maybe you can also show them how you more about the model repository and stuff like that.
Yeah. So what happens next while it's running? So we are going to get another experiment run just like this. So now the last major capability I previously mentioned was that we need to expose it to the end user, right, to the applications. And so the way we do it is that so it's actually moving the model to GPU now. So the way we do it is that we have a serving module. Oh, actually, I think this is going on now. Like, so we can see that the GPU was allocated, and it's actually the model is running and starting to use it. The only thing is that there's some delay here. We see it, right? So this first server, we see the allocation. So I think we requested 8 gigabytes of GPU memory. And so also we can see here, this is our job running. And yeah, so we saw the spike. This is how our allocation started to happening, right? And so we see a bump here, and then basically it's going to run for a few minutes, and then it's going to deallocate the GPU, release it back to the cluster so the other users can make use of it. So while it's doing that, let me show you how to deploy that model, right? So as part of the project we generate, there's a folder called serving. And so if we navigate in there, we can see a notebook where this is again something data scientists would do. They need to basically encode how they want the request to be processed, right? So there's a REST API request comes into this endpoint, and then they do some work to, for example, do feature engineering or do some transformation of the input and be able to reply with the model prediction, right? So the way this works is exactly the same. I just highlight this cell, and we wrote another plugin here for the inference deployment. And here we can specify like name of the endpoint, and then allocate resources on it. And when we deploy this, so this is again is going to run for some time, build the container, but then the container will come up and expose the REST API endpoint. Yeah, and so once again we have some API to track this, which will print the endpoint information, and that endpoint information can be passed to the consumer app. And that includes, of course, there's also authentication, so they need to know some credentials because the endpoint is protected. Okay. Yeah, so we can see that it's still, the job is still happily running, so it's completing the training. Yeah, and at some point it will basically deallocate the resources. So with that, let me give control back to Mohan, and we continue on the.
Thanks, Andre.
Yeah, sure.
So, share my screen again.
Juan, as you're sharing your screen, let's remind partners if they have any questions. It's really a great opportunity to take advantage of your subject matter expertise here and ask those questions, and even post some comments for you guys today.
Yeah, seeing my screen?
Yes, we are. Thank you.
Yes. Yeah. Yeah. So basically, this cluster we leverage it for our data for good projects in progress, and one of them is so we started this partnership with Georgia Tech, and specifically for their Knowledge Hub project, which is looking to basically promote sustainable development practices. So as part of that project, they are building a web platform which is going to promote the best practices and allow their consumers, which are primarily some sustainability startups, to easily discover information to help them with their growth. And that would include some basically will require some machine learning models, for example, to recommend them which resources to read, and also do any kind of exploration of their data and potentially build some advanced predictions about what they need to see, and like help in general discover their data. And as well as there's another project starting with UC Berkeley here. Okay, Teresa, do we have any questions?
We do not. Just again, a friendly reminder to let partners put questions in the Q&A. Let's go back to you, Andre. I see you have some conclusions that you want to follow up with the partners with today.
Sure, thank you. Yeah, so in this demo, we basically demonstrated how VMware Cloud Foundation can be used as a force for good. And then, end-to-end machine learning platform can effectively run on top of it. GPUs can be used to speed up model training, and a good thing is that they can also be shared to reduce the costs. We saw all of this is working on Kubernetes, right? So Kubernetes is perfectly, and specifically Tanzu, VMware Tanzu Kubernetes is a perfect platform for running AI/ML on VMware. Yeah, so it's in general, we are going to use this solution as a good proof that AI/ML is a good citizen on VMware Cloud Foundation.